Hi everyone, let's talk about why there are infinitely many prime numbers. Euclid proved this over 2,000 years ago, and we're going to be showing a variant of his technique. So first of all, we're going to need a lemma. We're going to prove that for all integers n, if n is greater than or equal to 2, then n has a prime factor. And this is going to be true by a proof by strong induction. So the base case is just n equals to 2, and that is a prime number. So 2 divides 2 works. 2 is just the prime factor of 2. Now for the induction hypothesis, what we're going to assume is that there exists an n in the integers greater than or equal to 2, such that 2, 3, 4, all the way through to n each have a prime factor. And now comes the tricky part. It's the inductive step. Here what we do is that what we want is that n plus 1 has a prime factor. So what we're going to do is that we're going to divide this into two cases, prime and composite. If n plus 1 equals to a prime, then we're done, because it's the same as the base case where n plus 1 is a prime factor of n plus 1. But if n is composite, then by definition there exists a k such that k is an integer between 2 and n plus 1 minus 1, which is n, because there has to be a factor other than 1 and n. We're going to call that k. But that's precisely the range in which the inductive hypothesis lies. So what we can do is that we can say that there exists a prime factor that divides k, and k divides n plus 1. So that leads to p divides n plus 1, and that completes the proof. So this tells us that every integer greater than or equal to 2 has a prime factor. And we're going to use that to prove Euclid's result. So Euclid's theorem says that there exists infinitely many primes. So we're just going to do a proof by contradiction. So suppose there exists finitely many primes, and we're going to call them P1, P2, P3, all the way through to, let's say, Pm. And P1 we can call it 2, since we know we can prove that 2 is a prime pretty easily. Here's the trick. We're going to let n be equal to P1 times P2 all the way through to Pm plus 1. So notice, if some pi divides n, then it also divides this over here, and that means not including the plus 1. So that would force that pi divides 1, and so pi equals to 1, but that's a contradiction. So that means that none of the pi divides n. So p1 does not divide n, p2 does not divide n, all the way through to pm does not divide n. But since 2 is in this list, we know that n is greater than or equal to 2 plus 1, which is equal to 3. So n has a prime factor by our lemma. So n has a prime factor, but it can't be any of these. That means there is another prime number outside of the original list that we had, which is a contradiction. And that completes the proof. And the last thing I want to say is that this proof can be generalized to certain cases of Euclid's theorem for primes and arithmetic progressions, and I'll make some videos about that in the future. Thanks for watching, and I'll see you next time.